Suppose you're a pharmaceutical company who has developed a new drug that combats epileptic seizures. The drug you develop works by terminating seizure activity by chemically interacting with neurons. You decide this medication should be taken orally, and so the drug goes to your intestine where it can diffuse into your blood. The blood carries the drug across the body and eventually to the brain. Once at the brain, you expect this drug to diffuse into target location, eventually terminating the seizure. But there are two problems with this method. One, most seizures only are active for a short period of time. By the time the drug is in your blood and delivered to the brain, the seizure will be long gone. Two, the brain contains a blood-brain barrier which prevents large hydrophilic molecules, such as your drug, from traversing through. One way to solve these problems is through a brain implant. Having direct access to the brain cells allows us to release drug at a moment's notice and to circumvent the blood-brain barrier entirely. For the implant, we can't just use any material. The material must be biocompatible, maintain a sterile environment, and be able to release drug. One such material is nanoporous gold-thin film. This material is made from gold, which has previously been shown to be biocompatible. But what's special about these thin films is the tiny nano-sized pores. These pores are so small that they prevent even the smallest of the viruses from going through, helping maintain a sterile environment. The pores are also useful because they can store your drug for release. Let's take a look at an example of our brain implant in action. When the patient gets a seizure, we can detect it by having nanoporous gold electrodes monitoring the activity of the neurons. As soon as we detect the seizure, we can send a signal to the same nanoporous gold, which releases the drug from the nanopores and into the brain. We now have stopped the seizure activity. Now, what if the patient has another seizure? We don't have any drug left in the nanoporous gold to release, so there must be a way to refill the thing. This is exactly where Implant diffusion comes into play. Assuming a distal reservoir with the drug and proper connection to nanoporous gold, we can diffuse the drug into the gold. This will effectively refill it. This sounds good in theory, but how do we implement this? To study this behavior, nanoporous gold is placed between two reservoirs, one containing pure ionic solution and the other containing a surrogate drug molecule. Over time, we can measure this diffusion by taking samples and measuring concentration. Plotting concentration over time gives us a detailed look into internal diffusion mechanism. Figuring this out brings us one step closer to developing an actual brain implant.